All right, hello everybody, and welcome to the third lecture in the first week of Physics 425, Low Temperature Physics. What we've been talking about recently are Stirling cryocoolers, and specifically what we thought about is doing work on a system, in our case an ideal gas, and using that work to extract a heat Q1 from a cold reservoir and then dump some heat Q2 into a hot reservoir. And that allowed us to maintain this temperature difference T2 and T1. So in a practical Stirling cryocooler, what you could actually do is you could run the type of cryocooler we've been talking about as stage 1, where you have some warm temperature T2 and a cool temperature T1. And then what you do is you add a second stage where T1 serves as the hot reservoir for the second stage. And then we have a cold reservoir, maybe at T0, and then there's some other work we do. And by that way, we can extend our temperature difference. So in a practical system, what you might have is T2 is around 300 Kelvin, and then T1 maybe gets you around 100 Kelvin, and T0 might get you to about 20 Kelvin. And so the question is, if you wanted to get below 20 Kelvin, what are the methods to do that? So we could run a two-stage Stirling cryocooler to get us to the 20 Kelvin. What do we do from there? And so that's the motivation for the next topic, which is called Joule-Thomson expansion. Oh. And actually the design of the apparatus shares some similar elements with the practical Stirling cycle that we thought about last time. So what we're going to have is something like a long tube. And we're going to make this tube insulating. So specifically, there's going to be no heat that enters or leaves through our tube walls. Okay, so it's not a metal, it's not a thermal conductor. And it's going to have one of these porous plugs that we talked about last time with the Stirling cryocooler. And so this is a porous plate. And what it does is it lets gas pass through but slowly. Right? If it's a really densely packed powder or something like that, the gas might get through, but it's not going to flow through easily. It's like a flow resistance. And in this way, it's going to act as a throttle. Okay, and like we had in our Stirling cryocooler design, we're going to have two pistons. All right, good. So let's just imagine that we try an experiment. And what we're going to do is we're going to start with all of the gas on, say, side 1, which is maybe the left side. And with piston 2, which is on the right, flush against our porous plug. Okay, the plug doesn't move, it's like a solid wall. All right, and so what that might look like, our starting conditions are, we've got our insulating tube, we have our porous plug, there's no gas on the right-hand side because our piston is right up against the plug. But over here, we've moved the piston on the left away from the plug. Call this piston 1. And so we have gas, like helium, on the left-hand side of our plug. And that gas is at a pressure P1, a volume V1, and a temperature T1. So we imagine an experiment in which piston 1 is used to push the gas through the plug such that P1 remains constant. Okay, if we want to make P1 stay constant as we move piston 1 to the right towards the plug, we're going to have to pull piston 2 away from the plug, and that will let some of the gas flow through. Okay, so simultaneously, we're going to use, let's say we take piston 2 and we pull it to the right such that the pressure on side 2 remains constant. And so, as we move piston 2 to the right and the gas enters the right-hand side, it'll be at some pressure. We'll call that pressure P2, and we're going to move these pistons in whatever way we have to, such that P1 on the left remains constant and P2 on the right remains constant. And we're going to do this such that the pressure P2 is less than the pressure P1. And so this is called a Joule-Thomson expansion. I think there's no P in Thompson. Joule-Thomson, which I'll call a JT expansion. Okay, at the end of our process, what we'll have is piston 1 is all the way up against the plug, and so all of the gas will have moved from the left-hand side, side 1, to the right-hand side, side 2. So at the end of the process, V1 is equal to 0, and all gas is on the right side with volume V2, pressure P2, and a temperature T2. So when we're done, what we've got is the following. Here's our rigid porous plug. Piston P1 is up against that plug. Piston 2 is over here somewhere, and all of the gas is on this side. So if we did this, what we would find is that sometimes, for certain initial conditions, the temperature T2 would be less than T1, So we would get cooling, which is what we are trying to do in this low temperature course. And for other initial conditions, we would find the opposite, that the gas is actually warmed up. So the result of the experiment is that T1 will not be equal to T2, but under some conditions, and so those conditions mean things like what temperature did the gas start at, what were the two pressures, P1 and P2, and so on. So under some conditions, gas has cooled, and under other conditions, the gas will have warmed up. So the goal of our analysis, which will start today and then probably finish next time, is we want to be able to understand this result. Can we come up with some kind of analysis that would tell us when we should expect the gas to cool and when we should expect the gas to heat up? Okay, so let's do some initial analysis. So external work on side 1. We're using a piston to compress the gas, so we're doing work on the gas. So the change in work is PdV. So this is simple because the pressure was constant, so we get minus P1, and our final volume was 0 because we ended up with the piston on side 1 right up against the plug, and initially we were at a volume V1, and so this is P1 V1, and so this is positive because we did external work on the gas to compress it. So I think before, when we were doing the Stirling analysis, maybe we were calculating the work by the gas. Here we're calculating the work on the gas by external mechanisms, and so that's the reason for the minus sign here. Okay, so that's on side 1. On side 2, it's the same deal. This was all done at a constant pressure, P2, and so the change in volume is V2 minus 0. So initially we had no gas on the right. And so what we end up with was minus P2 V2. This is negative because the gas this time does the work to push the piston. Okay, so the total work in our process, in our Joule-Thomson expansion, is the sum of these two. P1 V1 was the work on the left, and then minus P2 V2 was the work on the right. There's no heat exchange because we said the walls of our tube were not going to allow any heat to flow from the gas to the environment or vice versa. So this process is adiabatic since the tube is a thermal insulator. So if we think about internal energy, this is du is dq plus dw, where this is going to be the work on the gas, which we calculated. But because this is adiabatic, dq is 0, and so the change in internal energy is just the work. So the change in internal energy is U2 minus U1. And the work we just calculated above, it's right here. And so this is P1 V1 minus P2 V2. We can rearrange things so that everything with a subscript 1 is on one side and everything with a subscript 2 is on the other side. And we would find that U1 plus P1 V1 would have to be equal to U2 minus P2 V2. So what we found here is a conserved quantity. We do some process, and whatever this quantity, internal energy plus P times V, doesn't change when we had all the gas on side 1 compared to when it's all on side 2. This quantity, U plus PV, is called the enthalpy. It usually has the symbol H, and so this is called enthalpy. And what we found here is that this is a Joule-Thomson process, is a process of constant enthalpy, or it's isoenthalpic. So the Joule-Thomson expansion process is isoenthalpic. Constant enthalpy is all it means. Okay, so let's think about the case of an ideal gas. So Joule-Thomson expansion for an ideal gas. Okay, so we load our apparatus with helium-4, for example, and we say, well, okay, whatever process we use, right, whatever initial temperatures and whatever pressures P1 and P2 we decide to operate with, the enthalpy is not going to be changing. And so we have this conserved quantity. Okay, so the thing is, for an ideal gas, we know how to calculate these quantities. For an ideal gas, we know that U, the internal energy, is the number of degrees of freedom divided by 2 NkBT. For something like helium, F is going to be equal to 3. And we know from the ideal gas law that PV is NkT. So that means U plus PV is just going to be F over 2 plus 1 all times NkBT. So therefore we have that H is equal to U plus PV is F over 2 plus 1 NkBT, or it's F plus 2 over 2 NkBT. No gas leaves the tube during this process, so if we had N1 gas molecules or atoms initially on the left inside 1, when we're finished, the number of gas atoms on the right side 2 is the same number. So N1 is equal to N2. So that means if U1 plus P1 V1 is equal to U2 plus P2 V2, then F over 2 F plus 2 over 2 NKBT1 is equal to F plus 2 over 2 NKBT2, and we'll just make a note that N1 is equal to N2 is just going to be N. And of course, a lot of these things cancel, and we deduce that T1 is equal to T2. And so that's a problem, because what we said, or what I claimed, was that if you actually did this experiment, sometimes you would find that gas cools and sometimes you would find that it heats up, or specifically that T1 at least is not equal to T2. And so this analysis that we've just done implies that there's no change in temperature. The problem is that we started this analysis by assuming that we were working with an ideal gas. It turns out that the Joule-Thomson expansion, or specifically cooling by Joule-Thomson expansion, relies critically on the fact that the gas is not ideal. Specifically, we're going to have to consider how the gas particles interact with each other. In an ideal gas, you assume that the particles are non-interacting, except they only interact with the walls of the container that they're in. They don't interact with each other, so it's a dilute gas approximation. Okay, so the Joule-Thomson effect that we're trying to analyze relies critically on the non-ideal behavior of real gases. That is, the interactions between gas particles are important. All right, so let's think about that a little bit. Let's think, to make it simple, we'll start by thinking of just two particles that are interacting with one another. And the parameter that's going to be important is the distance between two particles. So let's consider the potential energy between a pair of particles separated by a distance x. Okay, and so schematically, we've got a couple of particles, and their center-to-center distance is x. Okay, the potential energy typically has, a shape like okay, so this is going to be the potential energy of interaction, and x is the distance between particles. So what the shape typically looks like is when the particles are very close together, there's a very high potential energy. Then it comes down and it goes through a minimum, and after going through the minimum, it asymptotically approaches 0. So that when the particles are very far apart, there is no potential energy. There's no interaction between those particles. Okay, now typically what will happen is a system will adjust until it minimizes the potential energy. And over here, we'll say this is x0 or something like that. This is like an equilibrium for the two-particle system. They minimize their potential energy when the distance between the two is x0. When you're over here to the left of x0, the particles are close together, and then they tend to repel one another. That is, they try to make the distance between them increase so that they tend to approach the x0. You can also think of like a ball rolling on this potential hill. The ball's going to roll towards the bottom of the well. And so in this region, this is a repulsive interaction between the pair of particles. Over here, the particles are very far apart, and there tends to be an attraction, so that again, if you're to the right of x0, the particles tend to move closer together to minimize the potential energy, and therefore x is going to decrease back towards x0. And so this is, on this side of x0, is an attractive interaction. Another way to think of this is, we know that force is related to potential energy via a position derivative. And so to the left of x0, the potential has a negative slope. And so when you evaluate du dx, you get a negative result. And so minus a negative result is a positive force. And so the positive force is x increases. So the distance between the particles tends to increase. Over here, to the right of x0, the potential has a positive slope. And so when you evaluate the derivative, you get a positive result. The minus sign out front of the force expression says that x would tend to decrease, and so it gets smaller, and it tends back towards x0. Okay. So let's see. In a real gas, we can write the internal energy of the system as some potential energy plus a kinetic energy. Let's just make a little aside here that in an ideal gas, when there are no interaction between particles, U potential is equal to 0, and the internal energy is all kinetic energy. Okay, so now we're trying to move beyond that simple model. Okay, so what we could do is we could say, let's suppose that we have a gas at P1, V1, T1. So this is our initial conditions for our Joule-Thomson expansion, and that the average separation between particles is x1. Okay, so on our picture here, maybe what we have is that initially we're over here at x1, okay? Okay, so what we do then is we do our Joule-Thomson expansion. So then the gas is expanded via a Joule-Thomson process such that the average separation becomes x2. All right, so after the expansion, the pressure P2, remember, was going to be less than P1. And so if there's less pressure, it's reasonable to expect that the average distance between particles has increased after the Joule-Thomson expansion. And so what you can see here is that there's been a change in the potential energy. So initially, we were over here at a potential energy U1, and over here, we're at a potential energy of U2. This was just for a pair of particles, but I think we can apply some reasoning here. And so, what we've seen is that the potential energy has changed. So, in fact, the potential energy's increased. It's become less negative from U1 to U2. So let me get my black marker back. Delta U potential energy has increased, right? It became less negative. So therefore, we expect that the kinetic energy, which we're using U kinetic for kinetic energy, if the potential energy has increased by conservation of energy, we should think that the kinetic energy should decrease by conservation of energy. And hence, because kinetic energy, temperature is defined as the average kinetic energy of the particles in your system. And so if the kinetic energy is decreasing, then we would expect the temperature to decrease and our gas cools. So that's one argument to suggest that our gas should cool after a Joule-Thomson expansion if we're including these non-ideal interactions between particles. But we claimed that if we were to do the experiment, we would say sometimes the gas cools, sometimes it actually warms. And so there's a second argument that we can try to make. However, there is a second mechanism to consider. During a collision, so let's imagine we have our interacting gas and there's a pair of particles that are going to collide. So during a collision between two gas particles, okay, so gas particles, kinetic energy is temporarily converted to potential energy, right? Because as the gas particles get very close to one another, the distance x gets small, the potential energy increases sharply. And if there's this big increase in potential energy, the particles are going to slow down as they get close to each other, and their kinetic energy is going to decrease. Okay, if the gas is expanded then we'd expect the rate of the collisions between individual particles in the gas should go down. So if the gas is expanded, we expect the rate of collisions to decrease. If the rate of collisions decreases, then how often we have this conversion of kinetic energy to potential energy will also decrease. And so that means when collision rate goes down, the amount of the amount of potential energy, the average potential energy in our system should go down. And so if the average potential energy goes down, the average kinetic energy goes up, and the gas should heat up. Therefore, would expect a net reduction in the average potential energy in the system. Therefore, the average kinetic energy increases, and we expect the temperature to increase. Gas warms. So we've presented two arguments, both of them on reasonable foundations. Argument 1 predicted the gas cooling. Argument 2 predicted the gas warming. And so conceptually, these two mechanisms compete with each other, and which one wins out in the end is going to be determined by the initial conditions of our system. So which of the two processes, one or two, dominates determines determines if a Joule-Thomson expansion heats or cools the gas. And so what we want to do is come up with a quantitative analysis to determine when we get cooling. All right. So in the experiment described, we can measure the following. We can measure the temperature of the gas and how it changes before and after, and we can measure the pressure of the gas on the two sides. And so what we're going to do is we're going to take this ratio of the change in temperature divided by the pressure difference, and we're going to define a coefficient. That coefficient is going to be called the Joule-Thomson coefficient. Usually it has the symbol mu, and so we'll put a subscript JT, and the way that we're going to define it is it's that ratio that we wrote in the limit that the pressure difference goes to 0. And so if we take that small limit, then the difference in temperature divided by the difference in pressure becomes this partial derivative. And we said that our process was going to be at constant enthalpy, and that didn't rely on the fact that we had our ideal gas. That was general. And so we'll use this H to indicate that this derivative has to be evaluated at constant enthalpy. Okay, let's see. P2 we said was always going to be less than P1. So P2 minus P1 is always a negative number. So if we want our gas to cool, we want T2 to be less than T1. So T2 minus T1 would also be negative for cooling. So we have a negative temperature difference divided by a negative pressure difference, and this coefficient would be positive. And so if this coefficient is positive, then T2 is less than T1 and we get cooling. And that's what we would like to have. If, on the other hand, the Joule-Thomson coefficient is negative, then the opposite is true, that T2 is greater than T1 and we have heating. So let's see if we can analyze this coefficient in more detail. So enthalpy, we wrote down enthalpy. We could express the enthalpy in terms of some thermodynamic variables, say temperature and pressure. And if we did that, then we could write a differential for the enthalpy. DH is going to be the partial derivative of H with respect to T at constant pressure times dt, plus a partial derivative of H with respect to pressure at a constant temperature times dP. But for our isoenthalpic process, dH must be equal to 0. Okay, so that means this is going to be a 0. And if that's true, 0 is equal to, let's divide by dP. So dH dt at constant pressure. And then we have dt divided by dP. And we only get dH equals 0 for a constant enthalpy process. So we'll put a little subscript H. And then we have still plus dH dP at constant temperature. All right, but you'll notice that, remember, our Joule-Thomson coefficient is dt dP at constant enthalpy. And so this is dP at constant enthalpy. This is our Joule-Thomson coefficient. Okay, so mu Joule-Thomson is dt dP at constant enthalpy, and that equals what? It's minus dH dP at constant temperature divided by dH dt at constant pressure. Okay, let's first work on the dH dt in the denominator. So let's work on the denominator. So enthalpy is internal energy plus PdV. So differential in enthalpy is du plus p dv plus v dp. But du is dq minus p dv. And so that means dh is equal to dq minus p dv plus p dv plus v dp. And so we get some nice cancellations. dq plus v dp. Okay. So then let's think about what we originally were trying to calculate is dH dt. So we're going to divide by dt, but remember, for the denominator, we had this at constant pressure. So if we have at constant pressure, the dP goes to 0 for constant pressure. So when we divide by a dt, we're going to get a dq dt at constant pressure. But think back to the definition of heat capacity or specific heat. Specific heat is the amount of heat that you have to add to a substance, say per unit mass, to change its temperature by a certain amount. So the change in heat divided by the change in temperature is heat capacity. And so this is a heat capacity at constant pressure. So this is heat capacity at constant pressure. That's convenient because that's something you could measure for a system. There's also the numerator that we could think about. Numerator. And I'm not going to do the derivation here. Maybe this is something we could talk about during the Zoom meeting. But what you can do is you can show that dH dP at constant temperature, and that's what our numerator is, dH dP at constant temperature. You can show that this is equal to volume minus temperature dV dt at constant pressure. Okay, and so when you combine these results, what we get is that our Joule-Thomson coefficient, which is dt dP at constant enthalpy, was originally written as minus dH dP at constant temperature, dH dt at constant pressure. And now we've worked on the numerator and denominator, and what we found for the numerator is T dV dt at constant pressure. I wrote that term first because there's a minus sign that's going to cancel the minus sign that we calculated for our numerator. And then we get minus volume, and then divided by the heat capacity at constant pressure. This is useful because all of the variables in this expression are measurable. So if you actually set up an experiment to do a Joule-Thomson expansion, you could measure all these variables and then calculate this coefficient. And if it's positive, you should expect cooling. If it's negative, you should expect heating. So I'll wrap up here just by saying that to go further, what we need is a model for the behavior of real gases. Or specifically, we need an equation of state. In fact, the first thing we'll do next time is we will start with the equation of state for an ideal gas and calculate the Joule-Thomson coefficient, and what we should find is that that coefficient is equal to 0, and so we get neither heating nor cooling. Then what we'll do is we'll adopt a model for a real interacting gas and see if we can determine when we should expect positive Joule-Thomson coefficients for cooling and when we should expect negative coefficients that correspond to heating. All right, perfect. Thank you very much, and we will see you next time.